Hey, what's up, guys? Yeah, so today I want to talk about the expectation value of the random walk. So this is like very simple results, but I often heard about people say this fact. So I want to make a short video say why this is true. Okay, so the starting point is a simple random walk. Okay, so let's consider one dimension. So the idea is that we consider all the integer points and with at the origin, and then you have a probability half go right, and then probability half go left. So it's like just the uniform random. And the fact that you may heard about people saying is that theorem. So the expectation value of the expectation value of this guy return to the origin. So return to the origin, or the number of times that this guy returned to the origin, it's infinity. Okay, so this just to say that I can define x to be the the number of this guy returned to the origin. Okay, so it's x is a random variable. Okay, and defined to be the number of times that this guy returned to the origin. So it's a random variable. Then I can ask the expectation value of this, and the answer will be infinity. Okay, and this is what we got to prove. And amazingly, is that in dimension 1 and 2, this expectation value, let's call x, will be infinity. But when d greater or equal to 3, this expectation value will be less than infinity. Okay, so this is what we're going to discuss. Okay, so let's just solve the one dimension case. Okay, so let's consider let's consider another simple another simple case. So let's only consider, in 2n steps. Okay, so basically, so n and a is just maybe 1 to 3 or something. So in 2n steps that you can go from the right and left, and I want to ask what's the probability that it return. What's the probability that it return to the origin after 2n steps? Okay, so I can ask the probability that this guy return to the origin. Okay, so this is very simple, right? Because in order to go to the from the origin, they must choose n steps to the right and another n steps to the left. Okay, so it's 2n choose n and the 2 to the 2n. Okay, and then one can use this Stirling formula. Okay, so Stirling formula tell you that n factorial is approximates square root of 2 pi n divided by e to the n. So 2n choose n is basically, by definition, is a 2n factorial n factorial square. So one can use this formula that I can get 4 pi n, 2n, e to n, and 2 pi n, n e to the n square. Okay, and that's 1 over 2 to the n, 2 to the n, 2 to the n. Okay, so you can simply see that this 2 to the n will cancel by this, and the e to the n will also cancel, and n to the n will also cancel. Okay, so your remaining will be pi n. Because this is 4, this is 2 square, will cancel. Right, so the answer will be 1 over pi n. Simple exercise. Okay. Okay, so I can ask the following: what is the expectation value of the number of times that it returned to the origin. Okay. So let's say v is the number of visits to the origin. This is simple, right? This is just by definition, it's just the summation of the probability that after 2n steps it becomes 0, right? Because it returns to the origin, that means that after two steps, after the first step, after 6 steps, then it returns to the origin. So it's at 2n steps. This guy returned to the origin. Okay, and n from 0 to n from 0 to n from 0 to infinity. Okay. Okay, and then we have proved that this is summation that it should be 1. Okay, n from 1 to infinity. Okay, because at the beginning origin, they already at the origin, so we should count only from n equals to 1 to infinity. Okay, so obviously that this is a p series. So it's 1 over square root of pi summation 1 over n squared n from 1 to infinity. So this guy will go to infinity. Okay, so recall in the calculus p series, we have infinity if p less or equal to 1. If p greater than 1, we have finite. Okay, and then you can prove this by using the integral test. Okay, so let's talk about a higher dimension. So in higher dimension, we can use the same formula, right? We have the expectation value to be the probability. So it's the probability of the 2n steps. This guy return to origin. But in higher dimension, let's say in 2 dimension, so this guy in each step it will randomly choose right or left or up or down. So the probability that it return to the origin should be this. Should be 2n choose n, right, by power d, because it has d choose, and it get 2 to n to d. Okay, so these guys is exactly this. Probably this is not exact answer, right? But the idea is that it's basically just the product of the higher dimensional one. Okay. So it's 1 over square root of pi to the d. Sorry, square root of n to the d. Okay, then let's neglect this 1 over square root of pi d. Okay, so the answer will be this. Okay, obviously this guy is finite if e choose to greater than 2. So that means d greater than equal to 3. If d less than 2, d less than equal to 2, then this guy will be finite. Will be infinite. Okay, so let's talk about scale. So in a 1D, what we gonna do is this series. Okay, so if you only do like the finite term, then this guy will be square root of k, right? Because you can approximate this guy to be 1 over k, 1 over square root of x dx. So it's 2 to the square root of k. Okay, so will be the order of square root of k. So actually, it's like a variance. So you can prove that the variance of basically the variance of the random walk is just sum over each steps. So you can get this kind of results. Okay, the 2 dimension, you get this because you get square root of n squared, so it's 1 over n. So this expectation value will be log n. Okay, so this is log n factor. Okay, and yeah, this is what I hope to show in this video. And basically, one can you can also ask that if it has probability p go to the right and the probability 1 minus p go to the left, then you can also do the same same analysis, right? So it's just interesting thing to investigate. And yeah, that's it. There are many kind of topic, but basically they all start from, I think, start from here. Okay, so just share with you guys. See you.